I'm going to do a little demonstration here with Mr. Bones. You ready? Ta-da! What happened? Nothing. What happened? Something. All right, what's going on here? Newton's first law is so famous that even middle schoolers and elementary school students can quote it all over the world. It says, an object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by an outside force. So everybody can quote it, but can you really say what it means? What it really means is that in order for an object to change how it's moving, you have to push or pull it. So a force is any kind of push or a pull. We'll get to that in the next video. But a force is required to get something to change how it's moving, to get it to accelerate. Things don't accelerate without a force on them. But it goes further than that too. There is not a single experiment in the universe that you can do to prove that you are standing still rather than moving in a straight line at a constant speed, at a constant velocity. If you can't tell the difference between those two things, they are effectively equivalent. They're the same thing. There isn't a spot in the universe that we can point to and say, hey, that's sitting still. Not even space, as I mentioned in our very first video about vectors. So that's what Newton's first law is. Newton didn't discover this law. When he put together his book Principia on how the universe works, he ordered them, and he has a famous quote. He says, "If I have seen far, it is only because I have stood on the shoulders of giants." The person who really proved the law of inertia first was Galileo Galilei, one of the giants who Newton based his work on. Now, I'm sure you've all seen the tablecloth trick, or some version of it, like this. Any object with mass will tend to resist any kind of change in motion, and the greater mass it has, the greater that resistance. But watch out for friction. That's an outside force. You're, of course, familiar with a variety of safety devices in your car, like, say, the seatbelt. This is an inertia stopping device, right? When you are in your car, you click it or tick it. And this seatbelt does what? If your car is in motion and you hit something, a U in motion tends to stay in motion unless acted upon by an outside force. So the seatbelt provides the outside force to slow you down along with the car. Here's another one, the headrest. A headrest is not for comfort. If you think about it, most of the chairs you sit in don't have headrests, and they're perfectly comfortable. Maybe not the chairs in school, but a lot of chairs are pretty comfortable even without a headrest. What is a headrest for? It's a matter of inertia. This time, it's not something to stop your head, it's something to make your head go. Alright, so imagine that this is your head and this is your neck and your spine and your back, okay? When you are in a car accident where you are rear-ended, if you did not have a headrest, what would happen? The chair is going to push your body forward, and a head at rest tends to stay at rest. From your perspective, it's going to feel like your head got jerked backward. But that's not what happened. Your head stayed still and your body got jerked forward. That can put huge strain on your neck. So the whole point of a headrest is to push your head along with your body so that you don't have your head at rest staying at rest. The headrest provides an outside force to keep your head moving along with the rest of the car. Of course, when you stop abruptly and you jerk forward like this, your chin hitting your chest helps do the same thing forward. You can still get whiplash, of course, but this makes it a lot safer and a lot less likely to be severe. Other features like airbags, crumple zones, and the fact that your motor is almost always put in front of the cabin, we'll talk about later when we deal with momentum and impulse. So this word inertia means the tendency of an object to resist acceleration. Something with more inertia is harder to push or pull. It's harder to speed up or slow down or change its direction. So things with large inertia, trains, planets, things like that. Things with tiny inertia, paper clips, mosquitoes, and so forth. There is a direct measurement of inertia that we call mass. Inertia is an object's resistance to a force, whereas mass is a measure of inertia. How do we know something has more inertia? Well, because it's harder to push or pull. It has more mass. Why do we say it has more mass? because it's harder to push or pull. This is an unsatisfactory circular definition, exactly as circular as the chemistry definition of mass. Mass is the amount of matter in an object. How do we know it's got more matter? Because there's more mass. How do we know there's more mass? Because there's more matter. Another circular definition. The exact nature of mass is something we'll touch on much, much later when we talk about the Higgs field in modern physics. In physics, to measure mass, we use the unit kilograms. Occasionally we will use grams, but in the MKS system, kilograms is the accepted unit. 1 kilogram of mass has a weight of about 2.2 pounds on Earth. That does not mean that kilograms are weight. Weight is different. Weight is the force of gravity. A 1 kilogram mass on the Earth, if you take it to the moon, it's still 1 kilogram, but it's no longer 2.2 pounds. It's 1/6 of that. So mass is measured in kilograms. This is a fundamental quantity. It's not derived from other things. It's not like meters per second, okay? It's like length or time or things like that. Mass is a property of matter, and that is measured in kilograms. So that's it. That's Newton's first law. Let's move on to the second law in the next video.